Abhishek, good morning. Can you hear me?
Good morning, sir. I can hear you. We will start within 5 minutes. So our
Okay, okay.
external speaker will be joining in 5 minutes. So
Okay,
we'll
no
start.
problem. Okay.
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 Abhishek sir, can you share the schedule, please, if possible?
Schedule is shared on the group. I think if you have joined the,
I joined late, so can you share it again if possible? Whenever it is convenient for you, just share it.
okay, I will share it again. Okay, so our external speaker has been joined. So now we formally start the inaugural session. So good morning, one and all. I am Dr. Abhishek Gupta, convener of this workshop. On behalf of CSIR Central Scientific Instruments Organization, Chandigarh, I welcome our chief guest, Professor Dinesh Kumar, Professor of Biomedical, RMIT University, Melbourne, Australia, Acting Head of Biomedical Instrumentation, Dr. Sanjeev Soni, the Coordinator of CSIR Integrated Skill Initiative, Dr. N.S. Jassal, and all the participants. I welcome all of you. It is my pleasure that we at Biomedical Instrumentation Group are organizing a 1 week workshop on artificial intelligence and computational imaging in healthcare under CSR Skill Initiative Program and partially sponsored by ICMR during November 17 to 21, 2025 at CSIR CSIO in online mode. We have received the registration for this workshop from 43 external participants from different variety of professions and institutions like PGI MER Chandigarh, Punjab University, VIT Bhopal, Sri Mata Vaishno Devi University, Katra, Central University Jammu, University of Jammu, Geetam Bangalore, Galgotia University, Netaji Subhash Chandra Bose, University of Technology, Shivnadar University, ACSIR, Indian Statistical Institute, and various CSIR laboratory like NPL, IM Jammu, CD Planning, IMT Bhubaneswar, and all. So participants from industry also like Infosys and like this. So it represents the participation from the various geography of India. This workshop offers a combination of academic, practical, and hands-on exposure to the field of artificial intelligence and computational imaging with medical applications. Experts are invited from foreign universities like RMIT University Australia and Indian Institute of National Repute like NIT Rourkela, PEC Chandigarh, SMBDU, and CSR CSIU Chandigarh. An industry person is also invited to take a few practical sessions. So we express our sincere gratitude to all our speakers. This workshop combines lecture and practical sessions. Every day, participants will attend 2 lecture and 2 hands-on sessions, providing both theoretical and practical knowledge. The lecture will be conducted based on practical applications in medical imaging and AI, while the practical sessions will expose the participants to developing their own skill or models in the field of medical imaging and AI. The practical sessions shall be conducted in Python, and therefore it is expected that each participant has the required facility to implement the required code. It is mandatory to all attend all the sessions carefully, and there will be a short and refreshing break after each session, and the certificate will be provided for all the participants who will attend all the sessions, theory as well as practical sessions. And the attendance of the sessions will be automatically monitored by the MS Team platform. So thank you and happy learning. So now I invite our acting head, Dr. Sanjeev Soni, who will address for this workshop. Dr. Soni, sir.
Hello, Abhishek, thanks. I'm audible?
Yes, sir, please.
Okay, so formally, I once again welcome all the invited speakers as well as participants on behalf of CSIU for this 5-day workshop on artificial intelligence and computational imaging in healthcare. So as you might have seen the brochure, so this workshop is basically sponsored by ICMR, including the CSIR Integrated Skill Initiative, and we have various sessions ranging from the principal component analysis, X-ray based anatomical predictions, then AI in healthcare, thermal imaging, multi-sensor gate analysis, then how to go for ML and DL in the low resource environments, terahertz imaging, as well as some other deep learning applications. So I just hope that this session will be really fruitful to the participants who are here for learning this. Only one request that be very much interactive in these online sessions, because we need to have a good connect, then only we can exchange the thoughts among ourselves. So with these few words, I wish all the best for this workshop. And I also thank the speakers who have accepted our invitation to give the lectures. Thank you. Thanks, Abhishek.
Thank you, sir. Thank you for addressing the participants. So now I invite Dr. N.S. Jassal, who is the coordinator of Skill India, CSR Skill India. So now he can address. Jassal, sir.
Thank you, Dr. Abhishek, Dr. Sanjeev Soni, and all dignitaries who are presenting here to contribute in this workshop in capacity of as a domain experts. And also thanks to all participants who registered for this workshop. And this is the second workshop that is CSIR conducting on this AI and computational imaging in healthcare. And that is very important area to just for the early diagnostic and right diagnostic for the further start the that is in the health treatment. So we definitely contributing in this skill development under this CSIR Integrated Skill Initiative program. And we are conducting so many workshops throughout the year. And if any participants in future also they wish to just attend this workshop, they can go through CSIR website. So these all efforts, I think all contribution that is made by Dr. Abhishek Gupta, and thanks to him also. And he is very dedicated for this second time also. And we are hope that in future we will definitely conduct third workshop of this domain also. So that's wish you good luck for the this success of workshop. And definitely I will also take one lecture on funding opportunity under prism scheme. If any innovator who have the idea and they wish to get the grant, then they can apply under prism scheme. So I will also aware about this scheme to the participants. So thanks once again, and good luck.
Thank you, sir. Thank you for motivating us. And this is worthful to mention that this is the second workshop on the same theme. And we will continue this theme next year also. So this is a sequential kind of workshop. So one workshop we have completed, and this is second workshop, and third workshop will be next year. around the same time. So now I invite our first speaker, Professor Dinesh Kumar. He is professor at RMIT University, Australia. So please, sir, Professor Dinesh Kumar, sir.
Hi, Abhishek, how are you?
Yes, sir. Good morning, sir.
Okay, now, how many are online and how many are physical?
Actually, this is an online workshop, and around 43 participants have registered for this workshop. Currently, around 24 participants have joined, and meanwhile, the remaining will also be joining. So, I think now you can start as your convenience.
Okay, I will put my PowerPoint up.
You can share the slides. Yes, sir.
Can you see me?
Yes, sir. You can do it in full slide mode.
Yep, I'm trying to do that. Yeah, okay.
Sir, good morning.
Yes.
Sukumar Tumnath from CSA CFTRI, Mysore. We just request that our expert kindly share your the notes or whatever are there, the PPT at the end of the. This is our request only, sir. Thank you very much.
Yes, sir.
Absolutely, no problems, no problems, no problems.
Yeah, at
Now,
the end of the
what I'm going to
workshop,
do is, thanks, Abhishek, for having invited me and everything else. And I hope you guys will not mind while I'm talking to you. I'm going to sip my cup of tea. It's 3 o'clock in the afternoon here, or 3:30. It's a good time for the cup of tea. Now, what I'll do is I'm going to share with you an example of a software as a medical device, SAMD, for AI in healthcare. Okay. So let's first begin with what is SAMD, software as medical device, which means that if I'm using a computer or a smartphone or anything like that, and if I am using that with a healthcare application, I call it as an SAMD, which has now become a global terminology for this particular kind of a device. So you can have computer decision making, you can have medical devices like that, and others. So the problem, of course, is that one of the good things is that SAMDs are very easy to make. You don't need any facility. You just buy a computer or you buy a smartphone, put the software on it, and bingo, it is working. Now, and thus it has got the potential of reducing the differences between the rich and the poor. You do not need a fancy lab. You do not need any of those things. Simply, you use a smartphone, which many people have, and using that, you put in some AI, and it works. There are millions of SAMDs around the world, but only a handful work. A handful of them are in use. Why? Now, I'm going to go to the next slide and come back to this one again. Again, AI in healthcare. Very easy to develop. Okay. How many of you in this room do not know ChatGPT? Anyone in the room who doesn't know ChatGPT? Who's never used it? DeepSeek. How many use that? Guys, we were going to be interactive.
I think, sir, all have used the ChatGPT and DeepSeek.
Okay. So you give ChatGPT a question. Does it ever tell you it doesn't know the answer? Yes, Smriti. Hi, Smriti. Then you,
Hello, Dinesh. Actually, I was about to say that DeepSeek is okay, but just using these technologies doesn't convey our or fulfill our requirement. We need to think even more and more about this one. These are
correct.
just transformation model, so we need to put some more intelligence in order to, I mean, get whatever we required as per our requirements.
Fantastic, Smriti. Thank you. That's so correct. The issue comes down to is that one is that they can be biased. Okay. Can anyone help me with the answer? Why? What do you mean by bias in an AI tool? Anyone among the 24 of you? No? Okay, we won't tell you the answer then. What do you think? What harm can be caused with a biased AI healthcare system? Okay, now let's make it easier. How many of the 24 in the room are men? All men, raise your hands. Okay. There are two men, so there are 22 girls. 3 men, okay. And 21 girls. Wow, I didn't realize that it was a very biased database towards the female gender in this room. Vishek, is that correct? They're in the room? Vishek, are you there?
Yes, sir. I'm here.
Okay, you are a man, right?
Yes, sir.
Then you didn't raise your hand. I said all the men in the classroom raise your hand.
Sorry.
So are there only 3 men in the entire room? 4?
Participant, please
Okay.
be interactive.
Well, Abhishek, we'll have to start with you. You'll have to be interactive too.
Yes, sir.
Okay. So what do we know now? How many people are men in the room? I can only see 4. Is that the correct number? 5, 6. Okay. Guys, if we have to make it fun, I can give the lecture and be done. If you want me to, you are not asking me to be interactive. I'm trying to be interactive with you. So obviously it is not working. Anyway, okay, I'll continue. So what harm can it cause? Can anyone give an answer to that?
Yeah, it will be kind of favoring towards only one condition, be it based on geographical area, be it as you took an example of gender biasness. So it would be that one only. I mean, bias, it resembles directly towards favoriting to one of the condition. And if you are saying what kind of harm it will be, if we are giving some output based on some biasness, then definitely it is going to favor one of the condition out of the complete box.
Right. Thank you, Smriti. So you see, if I am dealing with a situation which I was talking about gender, men and women, the problem comes down to is if I've got men, if I made a toolbox which is suitable for men, then it may or may not be suitable for females. if I've got a data which corresponds to brown men of India, it may not be suitable for white Scandinavian women. Hmm? It may not, if the database is for one kind of a body size. Again, all of these can result in biases. So how many of you are familiar with cholesterol? The word cholesterol.
Yes, we are.
Right. So, and in cholesterol, we know that cholesterol is considered to be having a problem with for the cardiovascular disease, right?
Well said.
If you consider that as a cardiovascular disease problem, and if you've got the issue, and if you don't, if you have the LDL greater than some amount and less than some amount, etc., it is supposed to be good or bad. You start taking in tablets, which has got side effects. The thing is that when this was done, this particular whole analysis was conducted in one suburbia of Baltimore City in United States. And in the process, the numbers that were got were suitable for a very German male population. Now, what happens? The same thing is being applied around the world and it does not work properly. Because the reason it doesn't work properly is because different body types are different. So the model is biased. It's biased towards a specific kind of a population. This can result in harm because you start giving medication to some people or you do not catch the symptom of some person. Let's have a look at now. Okay, so what I'm going to do is I'm going to give you an introduction, a background, and assessment tool technology, benefits, limitations, and some of the examples. So let's start with, I'm going to give you an example starting with Parkinson's disease. Parkinson's disease is a major neurological disorder. It is caused because of the basal ganglia, which you see in the red in the screen. And as a result of that, it becomes a multi-symptom disease with complex motor and non-motor symptoms. It is the cause of it is not known. There are no biological markers yet. The imaging techniques are also not being proven yet. PET, positron emission tomography, is considered the most suitable one. However, it is still being debated as to be for its suitability. And for all practical purposes, it is identified based upon the multi-symptom monitoring, which are clinical observations. One of the ideas is that it is related to the disruption of automatic movement and habitual tasks. So it's in the healthy basal ganglia, output is optimized for regular activities, while in people with Parkinson's disease, this optimization is impaired. Now, what happens is that this entire thing has got a number of motor symptoms, as you see: bradykinesia, which is slowness of movement, rigidity, gait abnormality, postural instability, impaired imbalance, speech, tremor, micrographia, and habitual actions, as I mentioned. Why does this now lend itself for AI and SAMD? So the concept of loss of habitual control is that there's an automatic movement control that is happening, which is managed by the basal ganglia. This may be central to the symptoms. But along with that are other things: the weakness, the bradykinesia, postural issues, and others. The problem now comes is that each of us are unique, are different. When we are unique and different, it means that every time I, as a neurologist, as a motor disorder specialist, meet a patient, I do not know how did the person speak before or now. I only know how the person is speaking now. I do not, many people speak softly, many people speak loudly. Many people have a squeaky tone, many people have some other kind of a tone. Again, weakness. Well, all of us have got different normal strength. Some of us go to the gym every day and have got the big muscles, and some people don't. So how do you simply say that this person has become weaker? Bradykinesia, not everyone runs like Usman Bolt. Some people are slow. Postural, well, typically not everyone has got the balance, and there is a difference there too. And again, about fatigue and everything else, and handwriting, which we mentioned in the previous slide. So how do you determine which one is a symptom and which one is natural? So the clinical challenge has become the variability of the symptoms, not only between patients, but also in the same day. So a person may have different symptoms in the morning and different in the afternoon. Effective medication can be different. Then the issue comes down to is how do you get the person monitored? Each time you have to monitor a patient, they have to go to the hospital. And that means that there is a long travel time, there is all the associated problems, financial and otherwise. And as a result of that, regular monitoring of this can be compromised. Regular monitoring we need to ensure that the system and the treatment is proper. So what does this all tell us? That means we want something, a tool, a software tool, which a person can do from their own homes. And we want to personalize it. We want to try and make sure that the tool is available for people, for each and every individual. How do I do that? Now, this is where the AI can come in. The challenges for AI, however, in the healthcare, it's a GIGO. It can be a GIGO. The issue is an AI tool. The good thing about AI tool is that it's easy to use. It's so easy to use, you give it to a monkey, the monkey will give you some answer. Does anyone know what GIGO means in this context? Someone? Okay, let me give an answer to the first. Yeah, yeah. Yeah,
Yes, sir.
I don't know your name. I can
So,
only say
sir,
DM.
sir, it will. Hello.
Yeah.
Yeah, sir. Sir, so it's about if you'll train something on poor quality of data, the output will be poor. That is garbage in and garbage out.
Correct. Thank you very much. And I was once in a meeting in Florida, and one gentleman, he's a senior professor at the University of Florida. He was talking to one of the young people, and he kept saying GIGO, and I did not understand. And then he explained it to me. He says, the good thing about the AI machine is that it'll always give you an answer. Whatever be the question, it'll have an answer. It'll have an answer. The problem is that answer may or you do not know whether the answer is correct or wrong. So if you are simply just using the GI in the AI tool with any data that you got, and you say, hey, I want to know something. It may have got no relationships, it will still give you an answer. Which means that an AI tool in healthcare or in other places as well, if not looked after properly, can be more of a problem than goodness. You have to be very, very careful. And more recently, in fact, just last week, we are using AI in everything. Last week, there was some newspaper article coming out of Pakistan where the person had generated the entire column from ChatGPT and forgotten to remove the line in the bottom. Now, by the way, I'm just admitting whoever is coming in. I don't know who's supposed to do it. So now what happens is that when I am looking at an AI tool to give me an answer, the answer of which I do not know, the probability is that I'll end up being stupid because I do not really know the answer. I put in something, I'm in a hurry, and I think this is a magic box which is going to give me an answer. And most of the times, you end up looking very silly. And that is what has happened to many, many AI applications. That is, that they put in something, there is a lot of noise, and then you realize that what you've got is garbage, and then people then run for cover. This is what I am trying to suggest. Let's not do that. Let's be careful by doing what we're doing properly. Okay, then. Okay. Now I'm talking about another issue with AI in healthcare. What are the problems? One is bias. What do I mean by the word bias? Said, yes, are you telling me the answer? I don't know the names, I only know SZ, I can see the initials. Yeah.
Yes, sir. The bias is like there may be demographic biases, like the location where a person is situated. There may be gender biases, age bias can be there, education bias can be there. So there can be many kinds of biases. In case of healthcare, uh, we can say the kind of place we are living may affect the kind of food we are eating, and like how is your background health. The age is very important bias in the case of healthcare problem, I can say.
Right. Fantastic. I didn't get your name. Shireen. Shireen?
Yes, sir. It is Shirin Zadu.
Shireen. Thank you, Shireen. Yes. So in healthcare, you can have all kinds of biases, and depending upon the question that you are asking. So now some of them may be long term. Say, for example, in general, most people don't get their gender change in a hurry, and their ethnicity also remains the same. Age, of course, adds on slowly. But then you also got the history of the family. So if you're looking at a population in Mexico, which has got the highest diabetic concentration in the world, compared to if you're considering countries, the Scandinavian countries, which have got a significantly lower diabetic association. What happens then? That means the entire data, if you train the data onto a Scandinavian database and take it to Mexico, obviously there is going to be a bias because the Scandinavian data has got a much lower percentage of people with diabetes compared to the ones in Mexico. So that would influence the outcomes of the model. If you are asking a model that is related to diabetes. Similarly, if I've got a population that is largely vegetarian compared to a population that is largely meat eating, again, I'm going to have a bias in some other disease, such as colon cancer. All right. So I have to not only look at the first order, but the second order. So I've got it. So I'm not going to be asking a question, does this person eat meat or not? The question is going to be, what are the probability of this person getting colon cancer? Suddenly now there comes a bias in the system. Similarly, if I'm looking at a community of people who are very active physically compared to another bunch of people who are leading very sedentary lives. A typical example is the Middle East, notorious for having sedentary lifestyle compared with people in Northern Europe, or who are known to be cycling enthusiasts. Obviously, there is a difference, and that reflects in cardiovascular diseases, right? The point I'm trying to make is that you do not only have to look at the first statement, the biases because of gender or of ethnicity. Yes, and please. And please, can you finger hands up? Was it by accident? Must have been an accident. Okay. So in the process, I am going to get a bias in the system. And in that kind of a situation, I would come up with misdiagnosis. So there was a recent case where there was a misdiagnosis of cancer in a university in London, and 2 people died. So you have to be very careful in this. And what does it mean in the long term? Okay. Any questions? Now, why do you think this happens? Can someone point me to the answer? Guys, I know it's morning for you, but you're not sleeping yet, are you? Is there anyone who's gonna give me an answer? Or at least Vishek? Let's hear it from you.
Yes, sir. Can you repeat the question? Actually, participants are also asking to repeat the question.
Okay, my question is written here. Why does bias happen in AI in healthcare?
Yeah, let me answer. What happened is sometimes we are targeting 4 categories, and we are giving excessive data into one category only, not considering other 3. So
Yes.
the AI model will think of the first category is prevalent, and will answer in the first category only. So this comes into the data when we are not giving the variety of data, or not giving the proper distribution of the data. Then the model also become biased and think of the answer is also must be in the prevalent category only. So it comes when the data distribution is not proper.
Correct. So you've got a situation where in any population, the healthy population is greater than the unhealthy population of a certain disease. Then That's one cause of the bias. The second cause of the bias is that different populations have got different disease characteristics and different parameters. So both of these create a cause of bias. And very often, people who are developing these AI models are computer scientists and not healthcare professionals. So a computer scientist often may look at the data as if it is just a data, while the clinical nuances are sometimes missing in such a situation. Thank you. Then there are some legal issues which come up. Who owns the data? You know, when you're talking about training of an AI model, we are using data. Who owns it? Anyone's got an opinion on it?
Actually, all the researchers wants data. Different stakeholders are there. Different industrialists even want in this area. Data they need. And in a nutshell, in the context of AI, if I'll say that the models need the data.
Who owns it?
Sir, I like to comment on this. In this, in healthcare, basically the data are patient oriented. So the ownership is with patient.
Anyone
Person per
else got
se
an
means
opinion?
the population.
Yeah, sure, understand. Does everyone agree with DM
Uh,
and Smriti?
Not always. Actually, we do get several reasons, like particularly rural areas or where the resource constraints are there. Uh, Usually, these data are kept under the surveillance of some community, NGOs or organizations. So they own data in those perspective. Of course, in the end, everything is owned by the patient only. Ethically, it will be
So
nice
so
only or correct,
so
but actually
so
community based it will be there.
So,
Okay,
as per the legislation in our country in India, the other whether it's a NGO or whether it's a developer or any healthcare setting, be it hospitals or anything, they are custodian of the data. But the ownership, as per the DPDP Act, or there are many legislation. I'm not going into detail in that, but the ownership rests with the patient only or the person whose healthcare data we are taking.
I agree. Ethically, it is correct, but actually on the ground, in the real pattern, realistic is this one only.
I do one thing. Can I, or as many of you can open your cameras or at least turn your microphones on? Let's have a 5 minutes conversation on this topic. Folks, okay. Come on, guys. Everyone, have your cup of tea and coffee and wake up. Right. Now, yeah, you can keep the camera on and then I can actually see people. Now, okay, tell me one thing. Why I agree that you think that the patient owns the data. How many of you are doctors? Medical doctors? Christian, you are a medical doctor?
Yes, sir.
Okay.
Yes, sir. I'm a ENT surgeon basically.
Okay. And you run a private practice?
Yes, sir.
Or you work for the government?
I'm into private practice.
Okay. So someone comes to you. I come to you as a patient. I pay you some money, right? Or the
Yes.
government pays you money on my behalf, depending upon whether I go public or private.
Yeah.
And your job is, my ear is got a problem, has got an insect has got inside. You go there, you do your procedure, and you pull out the insect, and you say there is a bill of 5,000 rupees. Okay? There's a
Okay.
transaction. You've done your work. I've got my reward. Right? Now,
Yeah.
Abhishek is a super duper computer scientist. He is looking for the data collected related to which insect goes in the right ear of people. All right. And
Yes. Yes, sir.
Shireen is there trying to build some kind of a AI model to predict whether if I am walking in the forest, which insect will go there and hence which medicine I should be carrying. Okay, I'm just making up some random example, all right? So Shireen,
Yeah.
I
Yeah.
know nothing about insects, by the way, and insects, thank goodness, and none has got into my ear. But let's take this as a case. Now, I have a problem for which I have given my money and I've got a solution. Krishna has got an expertise. He has got a client who gives the money, he solves his problem, and they are done. Right?
Yes, sir.
This whole interaction has got nothing to do with AI, has got nothing to do with Abhishek, has got nothing to do with Shireen. Abhishek now comes to you and he takes the data of your patient from you and using which Shireen builds the AI model. Right?
Exactly.
Now, Shireen has now gone to many people, built this AI model. And this AI model now is sitting on her laptop and it solves a real problem. So when Smriti goes to Shireen, she knows which side of the ear, which ear to look at for which insect. Okay?
Yeah.
Did you do anything extra for Shireen's model? You
Yeah.
got paid for your services from your client.
Yes.
And
Exactly.
that's it.
Exactly, sir.
That's it. End of the story, correct?
Yes, sir. Yes.
I had a problem. I went to my doctor. I got my services done. I paid for the services. End of the story. Who has made the
Exactly.
effort to make the model? Abhishek and Shireen.
Exactly, sir.
Neither me, Dinesh, nor you, Krishan.
Yes.
Right?
Yes, sir. Yes, sir. Exactly.
Are you seeing where I'm heading to?
Yes, sir.
Right. Now, once this is the case, then is it straightforward? I'm not saying the answer. I'm saying, is it straightforward to assume that I own the data?
Sir, I'd like to comment here.
No.
It's as per the discussion, it will be easier to assume that, but whatever be it WHO guideline or whether yesterday I was in a conference in Bangalore only, I was speaking on this only, I was a panelist there. So, as per all the legislations, if we want to use the data of the patients, we have to take the consent of the patient. Even if patient withdraws that I will not like the data to be used. Am I getting, sir?
Absolutely, I totally agree that you are referring to
Yeah.
not WHO guidelines, these are
So,
Helsinki
so
guidelines.
if patient wants that my data should not be used beyond this time or that, then we have to follow what patient. Uh, 1 minute, I'm getting lost. Uh, so we have to follow what patient wants because they are primarily the
Right,
it's all about the privacy and all. So we have to
right.
follow what
But
patient want
uh,
because the data
right,
ownership, as per the legislation of our country, is with the patient.
correct.
We are
In
merely the
fact,
custodian. We can use.
we we all are we all are under the Helsinki Accord of Human Experiments, and this is under what you're quoting is Helsinki Accord in 1986, redone in 2012, which is perfectly
Okay.
legitimate. But I'm not talking about privacy. Shireen doesn't know my name. She only knows that a male of this color and this age and went into the forest, and on the right ear the insect comes, and the left ear it doesn't come. That's all she knows. She doesn't know my name. She only knows. And if you now consider, so what I'm trying to tell you is that the answer is not straightforward. Then, and let's forget about the data. Now, Shireen somehow managed to steal your data, made a model. Okay. Now
Yes, sir.
you might, and she's been very unethical in the fact that she's stolen the data, not even told the doctor, and she's done it, and now she's got a model. What is a model? A model may be simply an equation, ax plus by plus cz is equal to x, right? That may be the model. Now she has already made the model. Okay? Who owns the model
Exactly.
now? Who owns the model?
So, model
He owns the
ownership
model.
can be with developer.
Right? So the point I'm trying to make in the entire scenario is, and Krishnan, what you have pointed out is perfectly legitimate. The thing is that while we are saying one thing, the courts are not agreeing with it. In fact, very recently there was a case where this is, even in this case, it is still more, inexact. One doctor collected the genetic data of a patient. That data was given by him or her to a company who used the data to create the gene modifier drug for that patient. Same patient. Okay? It's only 1-to-1. After having done that, then that company goes and sells the data, sells that pharmacy, the product to the same patient. The patient goes to the court and says, this person has developed this tool with my data. Hence, I am the owner of that. And the court says, no. Your data is, you have got some rights over it, but you're not the owner of it.
Sir, sir, regarding this, sir, I am practicing this in Apex Court of India, Supreme Court, we say. So, how law understand this in our country, and even I have been working with few people from WHO also. Recently, I was with one technical officer of WHO. She was a lawyer by profession. So, how our country understand in all the scenario in per se in our country, the ownership rests with the patient or the person whose data is there, even
Yes,
whether we have an
only,
MID or
Krishan, I totally agree
I'm not talking about
that it,
not talking about model or technology as such, but the data as such.
yep, I totally agree that that's on paper, it is true. But when you actually go into the court cases and you go through them, you find it is not straightforward. Okay. The point I'm trying to make for you is that the courts, the evolution in this space is so quick and sudden that most of the national bodies are yet and not have not come to terms to understanding the actual core principles behind this. So many times the the courts, such as whether the Supreme Court or any other court for the matter, I can only tell you that there appears to be some courts which are more traditional than the others. But the US courts are notorious nowadays of being less traditional and more towards the entrepreneur. The Australian and the European courts, and perhaps the Indian courts, are more towards the traditional method. However, the word data in itself is now getting argued. And the model in itself is now getting argued. The point in this entire exercise I'm trying to make for you is, I'm not saying I know the answer. I'm not a lawyer. Okay? I do sit on the TGA, the Ministry of Health in Australia, but despite that, what I can only tell you is it is not a black and white area. So when you are doing this, be mindful that it is, unless you have very deep pockets and you can get the best lawyers to fight your case in some big courts, the chances are that you will end up in confusion. So
Sir,
if you
one
can think
last
about
comment I would
this,
like to make here.
sure.
Always over the years 2030s, I am actually also, beside being a ENT surgeon, I am also practice medical legal consultant. So I am practicing medical legal law and all. So I have my own firm. So we see these kind of cases in our country, India per se. I'm primarily in the capital city, Delhi only. So what we have seen over the time, always law stays behind technology, and AI being a different technology compared to the other technology which has been integrated in the field of healthcare over the years, last 30 years, 20 years, not only in the uh, domain but also in the amount AI. So anyways, I always, whenever I speak, I always stress on that. No doubt our country, our legislation, our law will also evolve. Most of the countries law will evolve to accommodate that, but meanwhile 2 3 years, or meanwhile till we are not having any separate AI in healthcare act, and that will protect the rights of patient as well as clinicians as well as developers per se. So in the interest of all the three and balancing between all the three, so till then there will be a gray area only. But as of now, as per the legislation and how Indian courts understand, ownership rests with the patient per se, the person whose data is there. If someone is misusing or someone is using without consent, then they will be in trouble. Whether there, in our country there are many doctors who are developers, who have entered into developing so even if they are doing, they will be in trouble, or any outside developer, some data scientist or some other developer are doing this, they will be in trouble in our country per se.
I agree with your sentiments, and what I'll only say is that I do not know the answers. I do not know the answer for any part of the world. What I am giving a word of caution is, be aware
Exactly.
that it is not a straightforward thing. Be careful in how you manage it. And, again, someone the other day said, if I have used the data and to create in fact, my next slide was this. If I have created a model and if it works, most people will not bother to ask me, where did I create the model from? Okay. So now there are certain regulations. So for example, TGA in Australia, like FDA in the United States, asks you to define which model you have used to train your AI tool. However, even that is very difficult to manage. So the point comes down to is, but the other side of the story, so at the moment, globally speaking, India is one of the cheapest places to conduct experiments.
Exactly.
The reason, of course, we have people who have got a very low SDI, which means that they have got not only socio-economical indicators are low, and who are more willing to participate in experiments. Some of them may even be high-risk experiments. And coming out of India, it's still happening, unfortunately. However, when those kind of experiments are happening, you see, some of these are clinical data because I came on a regular visit to Krishnan and that data was collected because I paid for it and not the other way around. But there could be another thing that Krishnan wants my data, he pays me 5,000 rupees, collects the data and sells it to $5,000 to Shireen. Now, that's another complicated situation. But the problem is if we don't do that, currently, most of the data which is being generated globally is generated out of countries like the country representing the Northern Europe. Okay, typically and more often than not men. So as I say, more often than not, the data represents pale male stale or older white men. Now, the issue is if we don't release Indian data, all the products that are being made are not for the Indian population. Okay? But if you release it easily, the data is taken away and the model is sold back. Right? So the AI, again, so you have a question of if you want to remove the bias for people of Indian ethnicity, you have to share the data. But if you share the data and you don't get any credit for that, Shireen becomes a billionaire while Krishnan gets nothing out of it. Shireen, when you get the $1 billion, let me know, all right? So now, the point is that we have to have some data control, data management. And now I know that there are laws which say that data in India should only be saved on servers located in India. But we know that many of us would be using cloud services, would be using the Amazon or Google Drive or whatever we are using. And the data is not sitting on the Indian server for sure. Not only that, many of us ourselves, for literally a dinner, can give away the data of our friends and family and many others. It happens globally, and I'm sure it happens in India too. So all of these things mean that you just having laws in place are difficult because right now we are sitting on the internet right now and I could be sharing my data with you or I could be taking your data away, and it will be nearly impossible for someone sitting in some legal place in India or in Australia to check what is happening. It's very, very difficult. So the point I'm trying to make is that while we are going down this pathway, you will also have to think carefully in the present day scenario, okay, which means there is the potential of somewhere you got to store the data, somewhere you got to transmit the data, and then you only have a limited amount of funds to fight a big giant company. All of these mean that you have to have some kind of a data management strategy in place. And that would be something individual. I cannot, sitting here, judge and tell you what to do. So I think, Krishnan, you are a perfect example of a person who seems to be understanding the problem and knowing the rules. So maybe people like you and many more we need like that who can help. The government cannot do everything. Not in India, not in Australia, not anywhere in the world. Individual researchers and scientists and clinicians will need to take a lead path in this. Organizations such as CSIO would need to take a lead part in this. How do you do it? I do not know the answer directly. I can tell you what I do in my lab. But, so we definitely have got a way, and we're following the Australian guidelines of keeping the data on servers which are only located in Australia, because we need to get the TGA approval and we got to demonstrate that. So that's one thing we do. The second is that we also look at how we can manage the data of people without compromising their identity, and at the same time trying to encourage the would-be entrepreneurs, the would-be developers to go and take it to the next step so that they can get as much information as possible. Okay, and looking at my clock, I think I'm nearly done with the time. I'm only on my 7th slide. I've got 30 more to go.
So, you have sufficient time, sir. Till 11:15, we have scheduled this lecture. Till
Okay,
11:15.
What time is it now?
This is 10:50. You have another 20 minutes, sir.
No, well, I don't have to. I only have 5 minutes more for my next meeting, so I'll have to only. So what I'm
Okay.
going to do is that let me do one thing. Let me go back to my slides and see if there's something in this context, because there's no point in going into the details, which would not, then I would not be able to complete. Okay, let me not do that. That's going into the technology. Let's go back to this one. Okay, continuing on the questions. There's another particular question that comes up, and that is, what happens if the model doesn't work? So, Krishnan was a doctor. Amit was a patient. Shreen built the model, and Abhishek decided to use it on his patient. But the model gave way. The patient didn't. The patient died. Terrible, but it happened. All right. Who is going to be taken to the courts? So, Krishnan, that is one question which you may be able to answer better than I can. What happens now if something went wrong? Would the entrepreneur be the person? Would the clinician who's using it be the person? Would the doctor who gave the data, but now Shreen can say that the data was mislabeled. Are you the person who's the problem?
Sir, can you please repeat the first part of the question?
Okay. You see, let's say you are the doctor. You collected the data of a patient called Amit, who's on my screen next to you, by the way, Amit Chauhan.
Okay.
And Shreen used that to develop a model. And Abhishek is another doctor who used that model for his patient who came in. And that model gave a wrong answer. That wrong answer resulted in Abhishek's patient dying.
Okay, sir.
Now, then Shreen went into and did some homework and found that the data which Krishnan had given her was actually mislabeled. So it was, she made a model based upon Krishnan's expertise, but Krishnan had made a mistake, and so now who is the one who is responsible for all this?
So, sir, in this case, we have to understand it like that. I had given the data to developer, and the data was used to develop the model, and consequently the model was deployed after validation, and then this deployment results to the death of some patient, which was used by some other doctor, not me, because I had given the data, but the doctor was some other person. So in this, we have to understand three issues. One. One thing is, doctor who is using the technology will be responsible for any clinical decision which he or she has made. As of now, the evolution of the technology is there, but human in the loop model is always preferred and prioritized. So doctor has to follow their own instinct, their own clinical judgment while making any decision. That is one thing. So no doubt doctor will also be responsible, because his clinical judgment might not match what that model is telling or something like that. So doctor role will be that why you have not followed your instinct or your clinical judgment. Then it will come to the hospital who is deploying that technology, means healthcare setting, that whether you have trained your doctor and other staff to use that technology properly. Third, if the data was wrong or something like that, with then it will come to the developer will have their own responsibility, that whether the data was right or not, it's your instinct or your role to check the quality of data while using or before using. And uh, what about the validation, whether the validation was okay with the large set of patients? Because if validation is okay, the chance will be less that it will have such a complication that will lead to a death of the patient. So in this, each of the party, each of the stakeholder have their separate role. And if it's proven that developer has gone wrong in checking the quality of data before training the model, or while training, or while validation, they haven't ruled out any bias or something like that, then the developer will be held accountable.
Okay, a question then. How many of you doctors use a CT scan or MRI?
Most everyone must be using.
Right? Okay.
Hmm.
You know that I'm sure a CT scan is not an image. A CT scan is a scan developed by an AI model.
Okay, sir.
Correct? Do you agree with me?
Yes, sir.
An MRI is not an image. An MRI is a scan developed because of the magnetic resonance features of the body. It is not an image. It is developed by an AI model. Right? When you get a CT scan, you take a decision based upon the CT scan that you have got. You don't question that, do you? So when you get a CT scan or an MRI and you're taking a clinical decision, so Abhishek is the doctor who's taken a clinical decision based upon the MI model. How would then the person be held responsible for something which now has become common practice?
Sir, may I add something in this one?
No.
So, like these are the prevalent question which you are asking. So, for this one, a new concept came into the picture, that is a responsible AI. So currently, as per the responsible AI, whenever a AI model is coming into the practice, then there are certain rules. Like if that model fails, then who will be the responsible, who will be the accountable, and what are the methodology, like explainable AI has been used or not. So there are certain things. So if a doctor is using or a practitioner is using a particular AI model, so there are two things. One thing is that is a mistake made by the doctor. Another thing is there is some problem with that software. So if in the first occurrence the mistake done by the doctor, then doctor may be responsible. But the another thing is, if that is a software failure or software issue or any biases there, so the responsibility is already assigned, like who will be the responsible, who will be the accountable. So those persons will be captured for mishappening of these.
Right. I am not disagreeing with you. Responsible AI, as you say, or explainable AI, can only be in consideration when you are looking at AI like large language models or where a typical decision is being made, which is binary, which you can see. What I'm suggesting is if you go back and ask yourself a question, a CT scan, where the decision is being made by the AI for every pixel, the grain of every pixel, the value of the pixel is generated by AI, right? You do not have any explanation given on that. We've been using CT scans now since 1973, which is 1973 is 50 years. We have been using these tools. ECG machine that you use right now does a cleanup of your ECG using, again, machine learning. Your eye scans, all of these have got AI models. The point I'm trying to help you understand is that this is an important question, an important consideration. What Krishnan was talking about was exactly the whole thing is that in case if you are not careful, you are going to have the courts and make a mess of this whole thing. We have to be aware, we have to be careful as developers, and I'm referring to people like us who are largely in that space, as developers, to think and make a plan for how are we going to do it. And people like you sitting in the lead organization, the CSIO, would have to make a plan. One is education of the masses and other people, the developers and others. And the second is to have a plan on how you're going to manage these issues. The politicians do not know the answers. People like us have to generate the ideas and sell it to them. Okay? At the moment, in my opinion, having spoken on this topic across many conferences, I can tell you that we all are struggling to get the answer right. We do not want to we don't want everything to be delayed so that there is no progress at the same time. And we don't want things to go and everyone's, selling popcorn. We do not want the data only to have people of European descent, but we do not want the data of Indians to be misused to just train the models. Okay? All sides. At the moment, most data is biased towards men. We do not want that either. We want to include the female population as much as possible. All of these things are there, but if you are not careful, it's going to be misused. So there's a need for fine thinking and fine tuning of the model. I do not know the answer. I do not know the laws in India. I can also tell you that in Australia in itself, which is where this has been in discussion longer than most other parts of the world, still the answer is not clear. But we have to, it is a challenge we have to do. Okay? Then I think I have one more point which I can make in this time. Who gets the benefit of the model? So there is an AI model created for the healthcare. Shireen has made the AI model. We just now found that there was that all of us were running for cover when it came to someone dying. But now what happens is someone has come inside giving the 5,000 rupees for getting the treatment done. Who gets that? Who gets the benefit out of this? Who makes the money? Okay. Is it only Shireen? Or does she have to share it with the doctor who gave her the data? Or anyone else for that matter?
Collectively, all the stakeholders will be benefited, even the doctors, even
Yeah,
in some cases, we can say the patient will get the benefit as well.
yeah. So that means there has to be, that means the AI model in itself, the tool which comes out, has to have a verifiable history with it of how it came into being, right? Okay. So now there are a number of aspects that we've spoken about. One simple thing is, let's first talk about the problems and the benefits. Whoever's written the software may have done a good job or a bad job. All right? The model is perfect, everything is perfect, but the software didn't work because the software which Shireen wrote was bad. Shireen, don't take me personally, please. And so that one, when that happened, well, that is one problem. The second problem is that the data was not representing the patients. Then the third one, which I think Krishnan pointed out, is when Abhishek is a doctor, did he use that blindly, or did he use his own judgment? Then comes down to is, if he is using it blindly, did the patient know that that Abhishek was really not doing anything? It is simply the software that is doing the whole thing. So that means the patient should know the risk benefit analysis of that situation. So there are lots and lots of little tentacles which are going out. All right. Okay. I think it's my time to close my mouth. If you have any quick questions, please, I would be delighted to hear. I haven't heard most voices.
Any question from the participant side? I think most of the things has already been discussed, so there is no more question.
Thank you very much, Abhishek. Thank you very much
Thank,
for having me.
thank you, sir. Thank you for coming and delivering a insightful lecture. And you have discussed many things, and I hope this will be useful for all the participants. And thank you for accepting our invitation on a very short notice. Thank you, sir. Thank you very much, sir.
Thank you. Okay.
Okay, sir. Thank you. So, participants, now there is a short break, and we will start the next session by 11:30. So please join by 11:25, and we'll sharply start the new session at 11:30. So now you can have a short break. Thank you. Yeah, good morning, Professor Anup Nandy. Good morning, sir.
Sir, good morning. Am I audible?
Yes, sir. Yes, sir. How are you, sir?
I'm fine, sir. Thank you.
So, shall we start?
Yes, sir. I'll just share my screen.
Okay. Okay. Thank you, sir. So, with your permission, I am introducing our next speaker, Professor Anup Nandy. He is currently with the Department of Computer Science and Engineering, National Institute of Technology, Rourkela, NIT Rourkela. He serves as Head of Center for Automation Technology at NIT Rourkela. His area of interest includes artificial intelligence in healthcare applications, computing human cognition with EEG signals, human robot interaction with gesture, speech, emotion, and human gait analysis with deep learning techniques. He received an early career research award from SERV Government of India in 2017 year. He received the prestigious NVIDIA GPU Grant Award in year 2018 for his research on deep learning techniques in healthcare applications. He was selected as Indian Young Scientist in the thematic area of artificial intelligence to participate in 5th BRIC Conclave 2020 held at Russia from September 21 to 25, 2020. Further, he is a recipient of prestigious GSPS Fellowship from the Government of Japan in 2022. Among many, he has completed two bilateral projects funded by DST GSPS Japan and DST Ministry of Science and ICT of the Republic of Korea in joint collaboration with Tokyo University of Agriculture and Technology and Seoul National University in year 2019 and 2024 respectively. He is a senior member of IEEE. He has published a good number of research publications in reputed conferences and journals, namely IEEE Transition on Neural Systems and Rehabilitation Engineering, IEEE Transition on Cognitive and Developmental Systems, IEEE Transitions on Emerging Topics in Computational Intelligence. So with this expertise, I invite Professor Anup Nandy to deliver an expert talk. Thank you, sir. Please.
Okay, sir. Thank you so much. So, sir, can you just tell me my slides are changing?
Yes, sir. Yes, sir.
Okay, sir. Thank you.
Perfectly okay, sir.
Okay. So, I really thankful to the organizer for inviting me to give a session on the topic that I have chosen, that is AI-driven multi-sensor gait analysis in healthcare application. Mostly, I'll be talking about different type of sensors. And how you can be able to capture these human motions and these different techniques for analyzing the human motion for healthcare application. So what is the human gait? So the term the gait, it is actually the person manner of walking. As you can see in the figure, that when a person starts walking, so he is passing through different type of phases. So mainly this human gait is divided by two phases. One is called stance phase, another is called the swing phase. And in between the stance phase and swing phase, so there are different sub phases are there. There's a heel strike, loading response, mid tense, terminal stance, pre-swing, toe off. So these are the periodic motions of the human gait, and it is actually these person's gait pattern or the walking pattern will vary by different psychological and this physiological parameter also. A few of them, it is called person's height, weight, and their ratio, like body index, mass, and other parameters also, which is also play a very important role to in the walking pattern generation. So now, my objective today is to introduce these different type of AI techniques are available for doing the clinical gait analysis, and also some research work which my lab and my undergraduate students and these PhD students are currently working in this direction. So first is automated gate phase detection is a very important area of the research. So when a gate signal is given to you and how you can apply different techniques for finding this which phase the person is currently in. And there are different type of auto extraction of the features from the gate signal, whether it is a you are being captured from the IMU sensors or EMG sensors or 3D depth sensor. So mainly we are focusing on three different type of sensor as it is illustrated in figure 2. One is called EMG sensor. We are using Delsys Trigono sensors for capturing these surface muscles activations that has been captured from the various different persons, and it will help for identifying the different gate variation of a persons and for developing a decision support system. So second is called the IMU sensors. We are using this IMU sensor, so that has been also been procured. This is actually from the Sinner cell sensors. This is close to the Axion's dot that sensor. So we are using we are putting the IMU sensor in the different part of the lower limb, like in the thigh region and the shank region, and we are collecting this data accordingly for extracting the different features. Third one is we are using the 3D depth sensors. So that is a Intel 3D depth camera we are using for capturing the sagittal plane data and these frontal plane data. So we'll explain to you. And these are the different, AI can be used in healthcare application, that is various sensors that we can use in the different perspective, like this wireless accelerometer SU, or we can say this is a gate SU, which are available. Also, you can capture the data for the ground reaction force data, or this is GRF data, or you can use this is a pressure sensors to capture these pressures and to find out this person gate abnormality. So these are the different way of understanding the clinical gate analysis, exploiting different sensor data. So pathological gate detection, that is a very interesting area of research nowadays, and we can we can explore the different types of neuromusculoskeletal diseases. So like cerebral palsy, then we can have the Parkinson disease, and some other diseases is also available. There are some standard literature that we found, and where we identified that this is it actually needs in the current scenario to understand that is a why how to detect this pathological gate, and what are the precautionary measures that we can take up for doing say good prediction. So these are the different gate disabilities, so that most of you always aware about this is a cerebral ataxia, or then we have the Parkinson diseases, then we have CP gate, cerebral palsy gate, and this multiple sclerosis. So those are a combination of the neuromusculoskeletal disease, and every disease will have certain parameters which can characterize that particular gate, and our objective is to identify that particular features from the different type of sensors and extract some meaningful informations from the data and trying to predict. So it may be the vision based analysis, or it may be sensor based gate analysis. So these are the various sensors that which are available in my lab, and we are doing that is the different type of the human gate analysis, and we are applying different deep learning techniques for doing it. Like few of these sensors are called these ACMG sensors that is available. Then we are having these IMU sensors, then 3D depth sensor, and we are also using emotive neuro headset. So this emotive neuro headset, we are capturing this brain signal and trying to find the correlation of the human gait, because it will help for these older adults to find how these persons cognitive impairment will have impact on their gait analysis. So that is very interesting area of research. So this way that we can think of it to find a particular solution, so that it can be useful for them, because these older people are looking for a reliable solutions, so that they can do the home assessment, and we have already developed our device for it. That is a very easy assessment of the human gait, and it will just get the I will give the output of the gait variability. So this way that we can think of it to do the different type of research in that particular directions. And we are also having this now humanoid robot. So that is a bipedal locomotion. So we can capture this human gait and we can transfer this gait to this robot and how it will work. So this is another type of research. This is imitation learning. So now these are the different type of healthcare applications so that we can think of it by applying these different AI-driven multi-sensor gait analysis. One is called the early detection of the Parkinson disease. So that is it identifies what are the changes can be captured such as freezing, shuffling, and the reducing the arm swing. So these are the three important part. And another area that clinical gait analysis is called the post-stroke rehabilitation monitoring. So it will track this motor recovery, and you can find the gait symmetry. For understanding this gait symmetry, you can do for this vision-based approach or the sensor-based approach also. And this muscle activation pattern, for these things you can capture this different type of place. EMG sensor or surface EMG sensor DELSIS is a very state of the art and a very good type of sensor, that is a DELSIS trigono sensors, and it is actually used for the clinical gait biomechanics, and that we already captured the data from these DELSIS sensors, and we are trying to find this energy, that is a energy expenditure that has been captured from these ECG sensors. Another is called the orthopedic and post surgery, because it may so happen that when we are going to develop a like these orthotic structures for these lower limb amputees, then this orthotic structure can also be validated. You can validate these orthotic structures of the lower limb amputees or the upper limb amputee by developing some gait assessment tool so that it can be validated properly before applying it to a particular patient. So these are the different type of clinical applications, so we can think of it. And we can also go for some personalized treatment planning, like quantify the gait deviations. You can monitor these rehabilitation progress and so on and so forth. And it can also be useful for preventive healthcare, like for risk prediction for elder individual, and telemedicine based gait assessment, because remotely you can monitor and you can give recommendation for this home based gait depth camera and wearable IMU sensor. Also there is a continuous monitoring is also be possible where a different type of gait is being affected by these diabetics or a neuropathy or cerebral palsy, and there are other musculoskeletal disorders. So what is the objective of multi-sensor based gait analysis framework? So that this modern gait analysis, that is, it integrates different capture the different type of data from the multi-sensors, but so there is some gap is there, because we can capture this sensor data with different modalities now, and they are capturing from the different sampling rate. Now this is a main challenge. Then how we can synchronize this data? So suppose if I talk about this IMU sensor, so it will capture accelerometer and the gyroscope data for motion tracking segmentation. Whereas in the surface EMG sensor, it will measure the muscle activation to understand this neuromusculoskeletal coordination. In the depth camera, we are using Intel RealSense camera. For this, it will use for 3D skeleton tracking, and it will give the spatial gait information. And also these pressure sensors or the insole sensors, so it will record the force distribution and the ground reaction force. But all the data can be captured from the different sensors, and every sensors will have certain sampling rate. So our goal is that develop a multi-sensor framework, so to combine these multi-sensor streams to build a comprehensive gait representation, which can be useful for the diagnostic purposes and monitoring that how effective these multiple sensors or multi-sensor gait assessment tool can be useful for these persons who are having some gait difficulties. So the necessity is that this fusion is because this modality to capture different aspects, as I already told you. So integrating these heterogeneous signals through AI, that we have applied this AI technique for integrating all the sensors, which will have a comprehensive gait representation. So the key challenges that we face, that is called the time synchronization. As I already pointed out, That is a different sensor operate at different sampling, right? IMU sensor that is a 65 hertz. EMG sensor that we are using, it is a 4000 hertz, and depth sensor that we are using 60 frame rate per second, which it is required to alignment for meaningful analysis. So now what we have done, we have used simple techniques that is called this interpolation method to try to map this in this way, so that this time synchronization can be placed in such a way so that there will not be loss of the data. And also we have applied this noise and drift removal. So the real world data contains some artifacts. So we are using these different AI techniques to uh, refine these signals. And another important thing challenges is multimodal feature extraction. There are different type of features so that we can extract by using the deep learning. That is the temporal sequences of the gate. Then we have analyzed in these frequency features, spatial gate features. So this multimodal feature extraction, it's itself a challenging task. So we apply the deep learning method to do the same. So this core technical challenges is that in the sensor noise and the drift, because IMU suffer from bias drift that all of you know, and EMG suffers from the motion artifacts and electrodes. That's a, I mean electro and the electrode noise. And there is another core challenge is called the inter-subject variability, because because a person's different age, height, and weight, and the pathology and the walking speed, there will be large variation in the gait pattern. Another is called the environmental sensitivity, like these clothing variations of the persons and the occlusion and lighting condition, background cluttering, which really affect on the cellularity or the depth quality. So these are the challenges so that we face while doing the multi-sensor fusion network. And there is another thing is called the data modeling. One is called the temporal misalignment. That is because different sampling, how the different sampling rate, if you are going to capture, then how it can be combined in a accurate way so that it will have the good time synchronizations facility. Then another is called that is a limited level clinical data set. That is a medical data is very hard to collect, and they are unbalanced and openly very small. So that if you apply these very deep learning technique on the small, then it will be difficult for you to get the good results. And another important thing is called the nonlinear gate dynamics. So this nonlinear gate dynamics, it is a very important part of the research, because what we have done, we have modeled this gate by using the physics-based deep learning technique. Okay, so now physics-based, we have applied a Newtonian-based method and for understanding this human gait, and applying deep learning techniques or the generative AI techniques for doing these classification tasks. So that I'll also show you these results. So my first work that I'm going to tell, that is called the multi-sensor data acquisitions, and it is useful for gait health monitoring. We are using this IMU, EMG, depth sensors, that is a wearable sensors, and these are the experimental setup so that we have done in my laboratory. So there is a data collection protocol that you can see. There's an Intel RealSense camera, that is a D435i that we are using. We are using this Synersis IMU sensor. The IMU sensor has been placed in shank, and that is a thigh portion of a person. And we are using, this is a Trigano EMG sensor, and we try to collect this data. All sensors are time aligned using a common synchronization trigger. We are giving some abnormal activities so that the data collections can be done at the same time, and we can eliminate that frame. If you are doing some trigger, we are doing some triggering for making the same type the data will be recorded at the same time, so that there will not be any delay. But so delay was there, but we are trying to make it managing this delay, and so that we can get the very good results. So these are the way that we are capturing these data. And then after that, we have done some analysis that is called the gate phase analysis from the different phase that is being in the figures. If you see the figure 7, that is a different phase of the gate cycle from the collected IMU data. So we are divided into stance phase and the swing phase. So stance phase is a foot is in contact with the ground. That is called the stance phase, and swing phase is the foot moves forward. So in the red dot that you are seeing in the graph, so that is a hill strike. I mean, this point person start working. And that is a segmentation procedure. We are using some autocorrelation based technique to doing this segmentation method, and we are showing the results for this IMU data. So there are other sensor data also available, but we are not showing this data. So these are the different type of phases that we have divided: initial contact, loading response, mid stance, terminal instance, and the pre-swing. So we are using the SCM meter autocorrelation function. This is a very trivial technique, and it would be useful for doing this is a getting the very good results. And we obtained to identified that from different type of phases. Then we have done a data augmentation method for developing a healthcare model. We are using the gate rate dataset. So this ground reaction force, the gate rate dataset is very popularly known, and this is a very large dataset. And this is it is having this ground reaction force data for both healthy as well as the gait disorder patient. And this dataset has a metadata file which will have different type of features, that is a person's age, height, body weight, body mass, shoe size, affected size. So these are different 9 features of data metadata. So why do we require this data augmentation? Because medical gait data that is available have a limited sampling size, and so that it making robust model, we need a robust model for training. Training will be for the training purposes, it will be difficult for making this robust model. So there's another problem, is called the class imbalance. So class imbalance is a common problem between this healthy and the disorder gait. And there's another problem where the data augmentation is required. There is a high inter-subject variability. So there are many reasons which inspires us to apply the data augmentation method on this gate data set to get the good results. So now these are the models so that we have done, that is called this gate data generation. So we have generated this gate data by using the lightweight deep learning model, and that is we are applying some data augmentation technique. So there's a thing is that as you can see, we are using some metadata, and we are using a simple FNN generator. So in this generator that we are being used, it is a only very simple FNN, and which will generate a get sequences, and we are passing these get sequences to a encoder decoder model, autoencoder model. So the objective of using autoencoder is that for refining this gate and regenerating this synthetic gate, that and it will just matching this actual gate data, and then we have simulated this gate into a OpenSim simulation platform, because OpenSim is a very popular the simulation platform where you can simulate your gate after generating this data. So that we have used it we are using this very lightweight deep learning framework. By using the lightweight deep learning framework, we are generating this data, and we are trying to matching with this actual data, and we have simulated it on the OpenSim platform. So for these things, so what we have done some mathematical approach. So biomechanical foundation is that we have applied this Newtonian method, Newtonian modeling of the ground reaction force. This is very simple model, that is a force is equal to mass into acceleration. So this concept we have applied, and the parameters so that we have designed, and we have reconstructed this GRF, which must follow the loading unloading gate curve by using this FNN and autoencoder based technique and to matching with this actual data. So for this thing FNN based, so we have used a generative model for FNN based, and we have used FNN for generating the gate. That is the architecture, that is a FN generated output. So this way that we are generating this output, and we are using the metadata vector only. So total 9 features so that we have used for these 9 features along with this FNN. So it is generated this 101 normally stand phase GRF. And then we have used this autoencoder. Autoencoder is used for refinement of the data and reproduce this data, and which can also map to this actual data. So the objective of this lightweight generative model is that it removes this noise and it removes this unrealistic fluctuation, and so that we can get a good structures. And that is a model we have done. The validation can be done for the model output. We are using the 4.68 Newton bus, and also for this autoencoder after the refinement. So we are using 1.67 strong bus. So this is a standard method, and we have applied on the different persons, and we have obtained. So this value is this optimal value for doing this thing. So generated GRF, which satisfies this biomechanical force acceleration laws, and autoencoder it is provides this smooth and clinically realistic GRF data. So now, what motivates us to using a lightweight model? Because now you can see that everybody is going for a lightweight deep learning model or the lightweight physics-based deep learning model. And why lightweight? If the model is lightweight means you will have the very less number of parameters. Then you can easily deploy to a edge devices. So now this edge AI that we are also working in that directions particularly. So what is the what motivates us? Because if you simply use the traditional generative model like this GAN and this variation autoencoder and the transformer, it requires a large amount of data sets. And you need a powerful GPU-based system, and the training time is too long. So that's why we went for a lightweight model to solve all the limitation. So now the core idea of the lightweight deep learning model was that we are using FNN generator. It creates an initial gate waveform using only metadata. So it is one objective. Secondly, we are using the autoencoder. The objective of using autoencoder is to refine and smooth the waveform so that it can match with the real gate pattern. And another is they are using the very few parameters. So if you are using very few parameters, so the predictions that will be very fast, it is stable, and you can easily deploy it to any edge device. So that is the objective that we are using. So now the observation is that this comparison, as you can see, that is a this output that we are getting. The lightweight FNN and autoencoder model, you can generate this is your means real data that you can see that is given in the color, different color, and this is a refined data. After applying this FNN and autoencoder model, we are getting this good approximation. And before and after refinement, as you can see, FNN output, if you can simply, it will the dotted line is called this rough approximation of the GRF data. But after applying this autoencoder, this encoder decoder, the waveform becomes very smooth, and it is closely approximate to the real data. So this work is already been published in Journal of Biomechanics. This is a very good journal for the gate analysis. And these are the results so that we have obtained for checking this GRF consistency, that this FNN generator output, there is a mean deviation is 4.68 Newton, and refined output is 1.67. And it is acceptable threshold that we have checked. It is a 10% of the body weight of the person. If the person's weight is 70 kg, then it should be maximum deviation should be 7 Newton. But our result, as you can see, is 6.42. Similarly, for the other way also that we have checked it, that is for the refined output, and all the result passes this test. So these are the views that we have done, and these are the part. This work will have the great applications in the clinical and this healthcare impact, and it has got benefit, operational benefit, and also some this overall impact is the lightweight model. You can easily deploy it, and it is a scalable, and that can be useful in the real world healthcare application also. So my next work that I'm going to discuss is called the AI-based sensor fusion. How which fusion technique that we can plan to to get the data from the different sensor, extract the features, and apply the technique for fusing. But after fusing it, you can use it for this classification purposes. So we are using that is a taking this two type of data, that is called the IMU sensor data. It captures the segmental kinematics, that is the acceleration and the angular velocity, and another is called the ACMG sensor. So ACMG sensor captures this neuromuscular activation, and also we are using the depth camera. But in this work, so I'll show you this only this IMU and the ACMG. So it can integrate, it improves the robustness to noise, and that is it provide a meaningful fuse features. for downstream the deep learning model. So these are the data fusion model. We are using the move port dataset, that is a IMU and EMG. And here the healthy and unhealthy subject pairwise subject that we have used. And we are first using this is softmax normalization technique. Then we are passing it to the unsended Kalman filter. So there are different. So Kalman filter is a very good technique for fusing these information captured from the different sensors. So we are using this unsended. Why unsended? So I'll explain. So there is a Kalman filter, extended Kalman filter, and unsended Kalman filter. So there are different variation of the Kalman filter. So we are using unsended Kalman filter with BiLSTM model. So then we have the fused data. Then we are passing it simple FNN classifier to identify which one is a normal gate or which one is the variation of gate. And we validate this model by using a explainable AI techniques. So that is called the SHAP. So nowadays, whenever you would like to develop a model, whether you are using a generative AI model or any other model, so it is required to check the trustworthy. What is the trust of this model? For checking this trust of the model, we are using this explainable AI, that is called the SHAP. So SHAP is a very common technique that you can apply, and which will give the very good results. So now this intuition was that it is a nonlinear dynamical systems, and a linear Kalman filter it really struggles with this non-linearity. So we are using this unsended Kalman filter, which uses a sigma points to approximate the true distributions, and it will enabling for accurate fusion for the IMU and the CMG. So here there is a different state formulation you have to do, that is system dynamic measurement model and a sigma. These are the standard mathematical way. So why UKF for gate data? So it handles this nonlinear interaction between motion and the muscle activation. Second, it reduces the sensor noises, okay, while preserving the biomechanical meaning, and it produces this synchronized and temporality, synchronized sequences, which can be passed through a temporal deep learning model. So, and why BiLSTM that we have used? The objective of using BiLSTM is that is gate pattern depend on both past and future context. So keeping in mind, so the BiLSTM processes the data forward and the backward, which will capture the full stride dynamics. So these are the way that we have done. First, we have fused the data captured from the multi-sensor feature, that is UK, and BiLSTM extract the stride level temporal patterns. It will extract, then we are passing it through the FNN classifier and softmax level, then identify which one is a normal, which one is this abnormal. And we are using this SHAP interpretability for which will highlight these clinically relevant features. So these are the way that we have done, and it has got a very good impact and in the healthcare domain for early detection of the neurological disease, and the model, the AI model, so that you would like to develop, so that can be explainable and for checking the trustworthy decision quickly. And these are the outputs so that we have received, we have obtained, that is accuracy and the loss curve of this UK with BiLSTM data fusion. So these are the we are checking this model with different model, that is simple Kalman filter, that is the extended Kalman filter, and unsended with the BiLSTM. So there's a little improvement of the accuracy that we have obtained. So there's a next part is called deep learning for gate disorder detection. So that is also a very important research area. So we have explored different type of deep learning model for detecting the gate disorder. I'll first explain to you about this that is a image based technique. So now gate disorder classifications means we are doing this binary decision model, like whether a person is normal or whether a person is abnormal gate. Now this detects the how much deviations can be captured to find which can be useful for neurological orthopedic condition. So because I am executing one project with the DRDO, and there my objective is to validate the orthotic structures of the lower limb. So we have developed a software for that is called the gate assessment tool, and we'd like to uh, test the orthotic structure by using the software that we have developed. We have considered different type of sensors information from IMU data, then EMG data, 3D depth sensor data, and IMU plus EMG, IMU plus EMG plus 3D depth, EMG plus the 3D depth. Then we are trying to find that whether this the orthotic structure that has been developed, which is a problem in the fitment problem, or there is some other problem, but that person's after rehabilitation, when we declare this patient is perfectly okay, but how much okay this patient is there. So can I have some validation results? So the tool that we are developing that will help us to identify, yes, so this orthotic any orthotic structure so that you are having to be useful for the patient, so you can just check it. So these are the things. So I'm not going to show the software here. Here, that is the way that we are doing this work in this direction. So this gate disorder classification, that is a support the screening and diagnosis of the rehabilitation monitoring. So we are doing the gate phase detection. So it is very important part. Whenever we are doing some gate analysis, so phase detection is a first part. So we need to identify which one is a heel strike, which is toe out, mid stance, and the swing. Here we use the autocorrelation function to differentiate various gate phase, and it will also help to access the gate symmetry also. So there are different type of features. There are different types of features that we are using. So one is called the temporal features, another is called frequency features, and the image based feature. So for the temporal features, we are using this IMU sequences, and we are calculating the stride timing and the cycle progression. For the frequency based features, we are using EMG spectral energy and the wavelet coefficients. And image based, we are using the depth cellularity. And from the depth cellularity, we are calculating this gate energy image and this or gate energy map or this gate entropy map. So these are the different strategies that we have applied for identifying or for developing a classifications model to distinguish between a normal gate and this not abnormal, also it is called the gate variations. Okay, so so there are different, first work is called the gate energy and gate entropy based features for using the deep neural classifier. So there are different limitation of cellularity based. So if you are going for the 2D cellularity by G and GNI, that is RGB cellularities are highly sensitive to clothing. Second is illumination and background clutter. And there are different environmental factors also are there which will reduce the model robustness, and it will have in the real world clinical setting. So 2D cellularities, so it fails to capture the true 3D postures and the depth variations. So that's why we are used for the depth images. So it when I using the depth images, it provides the 3D spatial information, which is really robust, and it is invariant to lighting and the clothing. Second is it is captured. There is a fine grained motion pattern of limbs and torso, and it is really reliable for clinical gait abnormality detection. So key idea was there to capture this gait energy image and develop a depth gait energy image and depth gait entropy images, which can essentially extract the stable and dynamic gait cues for the depth frame. So these are the architecture so that we have used. That is we are using here squeeze and excitation based ResNet model. So to the objective is to preserve the ResNet model, to preserve the long-term dependency. So here what we are doing, we are using this depth map for the persons, and we are processing the data by applying different type of filters, and there we are doing the pairwise autocorrelation function for finding the gate cycle. Now the gate cycle that we are going to estimate, so for each gate cycle we are just calculating the depth gate energy image and a depth gate entropy image. Then this get energy image and the get entropy image is passing through the ResNet model, and the ResNet model that here we are using the different block that is called the squeeze and excitation blocks. I'll show you this why the squeeze and excitation block we are using. Then we are just going to do the classifications, and we are just plotting it. This is a GradCam visualization to find this temporal variability of the pattern in GI and the GENI. So there is a how you can be able to capture this depth gate energy image. So these are the formula. the or mathematical expression, that is a get energy image. It is represent this average posture across an entire gate cycle. So this way that we have calculated it, and we calculate this complete architecture and find these average postures. So what it will preserve, it will have, there is a two types of intensity. One is called the high intensity and it is called the low intensity. Now high intensity will explain the consistent posture region, that is a torso and hip. And in the low intensity, it is a high motion regions that will explain this arms and the legs. That is for the energy images, get energy images. So whereas in the entropy images, so in the get entropy image, it captured this pixel wise motion variability. So here this is more fine tuning and that is a more concrete information can be preserved by using this get entropy images. So it captures the pixel wise motion variability across this entire gate cycle. So that formula that we have used, and here high entropy, it is just this opposite of the gate energy images. As you can see in the entropy, is a high entropy will explain highly dynamic limbs, and in the low entropy, that is called the stable torso and the core posture. So then there are the two different models so that we are using. One is called the squeeze and excitation based gate CNN, that is called this convolutional neural net. So this is a lightweight CNN model for fast inference. Another is called we are using this deep ResNet model, that is a backbone with the squeeze and excitation attention model. So here we are using this attention model because it learns the channel wise importance. This is one part, that's why, and it enhances the discriminative gate region. So there are different parts of the human body, that is arm region, leg region, torso region. For these things, we have used some attention model, and which will help us to discriminate these gate regions. And it is really work fine for this squeeze and excitation block for both depth energies image and the depth gate entropy image. So this why we are using the attention model, that is it improves this gate reliability while focusing on this relevant part, that is the hip regions and the knee regions, arms, which part is it is moving, all the portions, so that we just attended and we focused so that we can get this good accuracy. So performance summary that we have used, depth gate energy image with this squeeze and excitation gate resonate, that we achieve very good accuracy 98.62. And whereas in the gate energy image, we are also having the good accuracy, but it is not better than this is a entropy based image. So this a lightweight model, it is giving this provides a good accuracy with a low computational cost. So this in an entropy image, it excels in capturing the dynamic, because in the GradCam images, so you can see, so it will capture this most dynamically abnormal gate pattern. Especially you can see, observe, there's a limb irregularity during the swing phase. So these features will overcome this illumination and the clothing challenges, and it is really important for clinical gate screening and home monitoring also. So as you can see from this outcome, that is a GradCam images from this both the gate entropy and this gate energy. So from the gate entropy, this limb irregularity part is totally, I mean, perfectly visible, whereas in the gate energy it is not visible. So it highlights this key region which is influencing the classification. It focuses on the knee, hip, and the limb swing, and it confirms this meaningful learning rather than the overfitting. So this gate entropy image, it will focus on physiologically relevant gate zone, which can be using for clinical interpretability. So we are extending this work to capturing this more data and exploring some other features also to be embedded. And our main objective is to, I mean, deploy these things to a edge AI devices so that it can be really useful for classification purpose. Next one that we are using some signal processing work. That is a limitation of using only temporal feature that you observe. That is, if you are using the GRF signals, which will contain both slow biomechanical trends and the rapid transition variation. So CNN easily extract the temporal patterns, but we may miss some high frequency gate events. So if we miss it, then it will reduce. It will lead to reduce this. It will lead to reduce robustness and there is a limited generalization ability. So that we attempted to combine CNN with these DWT features. So CNN captures the temporal structures of the gate shape, and DWT, why we use DWT, it extracts these frequency signatures like this hill strike peak and the loading rates, so on. And this combined features, it improves or it provides a good multi-domain representation features. So after combining these both the things, that is called a temporal embedding with this frequency coefficient, then we can pass it to this FNN for classification. So these are the model that we are using this GRF get data. As it is a imbalance data, we are using stratified 5-fold cross validation method. Then we are passing it through this CNN plus DWT, and this feature extraction can be done. And then we are using the classification by using this fully connected neural network to identify which one is a healthy gate and which one is a disorder gate. So this temporal feature extraction that we have done using 1D CNN, that is a simple 1D CNN that we have used, which is robust to inter-subject variability, and this it will learn that is a straight safe loading unloading curves and the impact transitions also, and it is good for this compact temporal feature. It represents this gate rhythm and symmetry and this loading curve structures also. So it is very useful in this case. So why we went for this DWT? Because this GRF, it contains rich high frequency component during hill strike and the toe up, so that we have observed. So this DWT, it separates, that is a low frequency and the high frequency details. So in the low frequency, this is approximate coefficient and a detail coefficient. So approximate coefficient means this is a global gate pattern, and this detail, that is called the sudden impact events. So it provides the better temporal frequency localization rather than the FFT. So this way that we have attempted to do, and we have achieved a very good classification accuracy, that is a CNN plus DWT plus FNN. We achieved a 96.22 accuracy, and we use stratified cross validation method to reduce this imbalance bias. And these techniques that we have applied with the different data sets, and we observe that is a reliable classification that can be measured for this identification of the neurological and the musculoskeletal gait disorder. So there's another work that we have done for the multimodal feature learning with TCN and CMS classification. So there was a limitation of the traditional CNN or this multi-layer perceptron. So what was the things that CNN captures only the spatial or temporal structures, but it ignored gate similarity relations. Okay, in order to preserve the pairwise similarity, so we apply this CMS neural network. So that is also very new techniques so that we are applying. So, and we are using a temporal convolution neural network. The objective of using temporal convolution neural network is that it extract the multi-scale temporal dependency, and you are trying to do some pairwise similarity between the healthy and the abnormal gait. So this multi-domain features learning combine temporal features plus frequency features plus similarity. So this instead of classifying directly, this Siamese network, it learns how similar is the gate signal to a healthy reference. So that we have done it. So this is the block diagram, as you can see, that is a healthy gate data set. Then we are using gate cycle. Then we are generating this abnormal gate data by introducing a phase lag, and we are passing and the abnormal gate data has been generated, and it is passing with different type of feature extractions. Okay, like frequency based feature. Then we have done these merge features. Then we have done some feature selection method. We are using the Boruta method. This is some statistical technique that using for feature selection. Then we are passing it these features to a TCNN and CMS network to identify which one is a normal gate, which one is a abnormal gate. So that is a this TCN, it will capture both short range and the long range gate dependency. And multi-scale features, it will represent the loading rate, foot strike impact, and the multi-strand stability. So these temporal features and the frequency features, it is really important to capture so that we can find these what are the irregularities are involved in the abnormal gate, which can easily be extracted and which can also be focused, and it will can be used. The objective of using the fusion is that it concatenates this TCN temporal embedding with the frequency domain, so that we can get it better accuracy. This is a why CMS, because it learns the relationship that is from the healthy to abnormal, or the abnormal to healthy, or healthy. So that is called the gate similarity, and it will reduce the dependency on the large level data set. So for these things, we are using this CMS network, and we achieved the very good accuracy, that is a 98.21% by using this multi-domain feature like TCN with this CMS network. This CMS actually CMS learning improves these generalizations for unseen subject by focusing this only similarity distances, and TCN that we can use with the mind that it will capture the multi-scale gate rhythm, which will have impact more effectively than the LSTM and this CNN. So next and the last work, so that I'm going to show, this is called, another things is that there is a energy based features, because as you know, there's a human gate, it is a the spatiotemporal pattern, and whenever we are trying to understand this gate variability of the different persons from the normal persons and the abnormal persons, so energy is very important. It means how much energy that is being involved, or how much, if you try to find this energy expenditure, which will help us to model this gate in such a way that this we can easily identify this abnormal gate or variation in the gate pattern. So that's why we are using a energy based feature analysis. This is very new technique, so that we applied, that is called the self attention based convolutional restricted Boltzmann machine. So from the restricted Boltzmann machine, this is very standard one, a restricted Boltzmann machine. So we are using the three part. One is called the convolution part, another is called the energy function, and another is called the self attention. So to extract the robust and physiologically meaningful gate feature, we are trying to extract the energy feature. So why energy based modeling is important? Because in the standard features extracted, which fail to model the energy distribution. Okay, and if you simply extract this CNN, it extracts the spatiotemporal pattern, but it ignores the probabilistic structures of the gate signal. And there are a lot of transparency. Lack of transparency will reduce the clinical acceptance also. So that we went for the applying the energy-based modeling, which will launch the hidden dependency between force pattern in the gate cycle. And why we use restricted Boltzmann principle? The objective of using restricted Boltzmann principle is to capture the global gate structures. And the self-attention mechanism, why? Because the self-attention enhances this long-range temporal relationship. So for these things, we extract the energy distribution, energy features, and find out the energy expenditure, and we taken into consideration it, and we are just classified. So these are the diagram that how the energy based feature analysis that we have. This is called the ScrapNet. We have named this as a ScrapNet. We are using this same GRF data, that is a gate reg data, and the feature has been extracted using the self attention based convolution restricted Boltzmann machine. And these extracted features, so we have applied variational autoencoder for reducing the dimension, and then the reducing features is used for finding this is a interpretability, like this explainable AI. And with the extracted features which is coming from the self attention based convolution restricted Boltzmann machine, we are using this simply FNN model to classify whether it is a normal gate or it is an abnormal gate. So these are the core component mathematical part, that is a 1D CNN, that is it learns the local GRF structures. Self attention model, we are using the self attention model for long range dependency. And energy functions, this is a restricted Boltzmann machine based latent features modeling. So here that is a in the higher dimensional vector 2, we are going to analyze in into a lower dimensional, that is a need lattice space. And these energy functions is really give us a very good results for understanding these energy distributions, and we can model it by using the probabilistic distribution function, that is in the Boltzmann form. And from the GRF input, we are passing it to the convolution, then self-attention, then energy sampling. Then we can finally construct the feature vector. So these are the way. While self-attention, I already explained. So these are the accuracy that we obtained. That is a 93.47% for the training accuracy, and testing is 93.17. And these are the performance metrics. And these energy-based features, it captures these inherent biomechanical deviations, and for these things, and it will have a great impact in clinical gait analysis also. And for the explainability, that we have applied this SHAP-based technique, and there is a different mathematical variation. I mean, it is already available. The SHAP confirms actually the ScrapNet learns, physiologically meaningful gait features. So that is why healthcare needs this AI-driven gait analysis, because gait it is an early biomarker for neurological, metabolic, and orthopedic condition. So multi-sensor systems, it will easily detect that is how much deviations is there, which cannot be visible by the human eye. So ensembling it enables and quantitative monitoring, so you can easily do the good assessment. So there are different domains of application that we can highlight. That is called the neurological disorder like Parkinson and stroke, chronic metabolic conditions, that is orthopedic and post-surgery, elderly, fall risks, that is a very good research area, and sports injury evaluation like ACL injuries, if we can think of, that is a anterior cruciate ligament. So these injuries, you can do early detections or the predictions algorithm for applying the different machine learning or deep learning techniques to do the same. So Parkinson disease detection, so you can have detect this gait freezing, and then reduce this is a stride length, arm length, and you can do some different type of fusion also. And you can find out these depth-based gait features to help quantify the motor degradation. For the sports injury, I already explained, this is ACL injury. And fall risks, that you can apply these depth and eye move systems, which can be detect and find this stride variability. So this technique, fall risk detection technique, are really useful for elderly care. So as I was explaining in my the first slides, or a few introductory slides, that collecting the data from the human brain, and if you can connect it through the gait cycle or this gait pattern, and you can understand that how much attention is required for the older adults to resist or to prevent these fall risks. So that is the things, and also the how the cognitive impairment will influence this person walking pattern. So this is a very interesting area of study, where the mind, and that is called the how finding a relationship between this gait and the human mind. So these are the very new area of research, so that we can have. So conclusion, that summary of my technical contribution is that I have explained multi-sensor based fusion for using IMU, EMG, and the depth sensor, which may be useful for a unified biomechanical representation. I have explained different AI-driven model, CNN, DWT, TCN, and CMS, and the ScrapNet, how to extract the multi-domain features, and how it can be useful for identifying binary classification technique. Then I have explained this a lightweight gate generation model which supports the augmentation and biomechanical validation. Another is called the explainability. Explainability for AI, we can use SAP and the GradCam method for improving the clinical transparency and the trust. So there's a great impact of this healthcare. That is it enables the early detections. Second is personalization, supports this personalized rehabilitation, and it will reduce the dependency on the expensive gate labs. Okay, so these are the future directions. I think so. This is my last slide. So this is a future direction of the AI-driven gate healthcare. That is digital twins of human gate. So this is a very interesting area of research, where the real-time biomechanical simulations of for therapy planning and this gate anomaly prediction, real-time smart home gate monitoring. You can use depth camera on the wearable for continuous for this. We have developed a recently developed a device for smart wearable uh, gate detections device. Okay, so you'll have a only low cost IMU sensors. Person will be wearing the IMU sensor. It will collect the data wirelessly, and it will our device will capture this data, and it will check display this whether any gate variation is there or not. So we have deployed the lightweight model onto the edge devices, and it will do the very fast results. So that is for the home assessment. So no need to visit. No need to access any very high-end, high-cost gate lab. Only small and portable devices may be useful. So we are in the way to submit it for the patent applications, and then let's see how these devices will work. And last one is called the personalized and assistive healthcare. So that is also a very interesting area of research that can be useful for the rehabilitation programs, where this AI will adjust this therapy intensity based on gait recovery metrics. And another is called, that is a wearable exoskeleton. So now people are working to develop a very lightweight exoskeleton. So lightweight exoskeleton it is a really challenging task. And after rehabilitation, how much recovery has been done, or how much recovery has been made. So that assessment is really important. Okay, so for this thing, so there are a lot of tools are also available. Then some generative AI based tool is also developing, and people can also check it how it can run. So thank you so much for your kind attentions and attending these sessions. So if you have any questions, so I'll try to respond to these questions. Thank you.
Thank you, sir. So from the participant side, if any question is there. Yes, sir. Sir, I have one question. You have explained the gate analysis and all. So, is
Yes,
there
sir.
any analysis is it done like correlation is done with the brain MRI? Like if we have the one brain MRI of the patient and have done some gate analysis, so any correlation has been established or some study? Can you explore on this? Can you say something about it?
No, sir, actually, so this is a very interesting question. So till now, sir, I haven't found any, because brain MRI, it is a different part, isolated part, and this analysis of the human gait using the different sensors. So that is a two different other domains. And I haven't found any kind of, because in a separate study can be done. But I was explaining you, a person is wearing the headset, at that time person is walking on the treadmill, okay, or any flatter region. So that data set is available, but the data that the questions you are asking, I haven't found that this is a MRI. It is a separate study. You need to have the fMRI devices and scanner, and at that time you are not in a position to collect the data. Collect this gate data. Okay, so there may be some offline study. You can take the data offline mode, and after getting the data from the fMRI, then you can find these biomarkers of these human brain, and from this particular biomarkers you can relate it to a particular gate signal. So that offline mapping that has to be done in intermediate side.
So
Okay.
like such type of a study where like the same participants have been fMRI has been taken of the same participant, and then in the another instance for the same participants the gate analysis has been done and then some correlation like that
Yes,
type
yes,
of
yes.
study exists?
Correct, sir. So that can be done. So before that, what you have to do? So you have to just do some identifying that biomarkers of the persons of the human brain before doing the MRI data or before doing this MRI. Then after that, when the MRI will be done, then from the images, then you have to extract that feature which will characterize these particular biomarkers. Then it will be very easy for you to find the correlation between this human gate and the brain side. So that is very interesting area of research and very complex study. Okay, to do in that direction.
Yeah, actually, initially, like some time ago, I also thought of doing like this type of a study, but the lacking part was like data was I did not find any data. So now I heard about your experiment. So I thought like if you are aware about any data, we can get and we can do some analysis on that. So if you can,
Sir, actually, I'll see because I'll having some different collaboration with the foreign university and
okay,
some I'll ask them, sir. And if possibly, if there is some data is available, sir, I'll just means let you
sure, sir,
inform, sir.
sure, sir, sure, sir. And any and the another question like for this gate analysis, any the product or any like as you said like lightweight exoskeleton you are developing or the type of devices you are developing. So currently, is there any device available in the market or company is producing for the public use or this is in the research phase only?
Sir, actually, I am not developing any exoskeleton device. Actually, I am developing a very smart, means wearable, portable, small device for assessment of the human gait. The
Okay,
exoskeleton, because I am associated with DRDO lab, because I am executing one project, so they have developed a one exoskeleton. Okay, so my objective is to validate this exoskeleton to this efficiency of the exoskeleton structures by using this this AI assessment tool. Okay, but sir, there are a lot of exoskeleton are available in the market, but they are not very lightweighted exoskeleton. I think because it is very because very heavy weighted exoskeleton available. But at present, I don't remember the name of these things, sir. But I can tell you, if I contact these scientists in the DRDO lab, so there are already available exoskeleton is there, sir. And that are also being used for post-stroke rehabilitation purposes, because this post-stroke rehabilitation is a very good area of research in that particular direction, and people are developing this exoskeleton, trying to develop. So that can also be useful, sir.
okay.
Yes, sir. Very,
Thank
very
you, sir.
good question.
Thank you, sir. Thank you. And one question in the comment, if I can, Krishna Priya, I think Dr. Krishna Priya, you can read your question. You can ask your question, or should I ask your question?
Yes, sir, I can see this question. That is, she's asking, how can we analysis get using 2D sagittal and the frontal video without any markers, I think, or the sensors of the subject? Yes, so that is a very good question. Okay, so actually, madam, the thing is that from the 2D data, if you can see the previous analysis in this 2010 or 2015 work, so people used to do these 2D celluloid images. Okay, so from these celluloid images, from the images, it is very difficult to identify which one is the left leg, which one is the right leg. So what we have to do, we are at that time we just trying to find that is a body aspect ratio of these persons. Okay, how much distance from this shoulder to elbow or elbow to wrist, all other things by the pixel, and from this pixel we are trying to find some coordinate position. Okay, from these coordinate positions, you can do some stick model. Like in the Kinect, if you see the Microsoft Kinect device, from the Kinect, you can get two different type of get data. One is called the skeleton data. So from the skeleton data, you can able to see different joint coordinates are available. From the joint coordinates position X, Y, Z, you can calculate this joint angle. And Kinect is also give it to the some 3D, depth information. Some cloud map is also given. So from the 2D data, either you can go for this Microsoft Kinect. From this Kinect data, you can easily get this skeleton data. Actually, skeleton data is actually coming from the depth images. It will just subtract this background, and you are going to see this person's only that particular portion of the human body while this walking. Or else what you can do, you can just simply doing some kind of color marks. Obviously, so biomarkers is required in this case, that different type of colors. From this color you can find this coordinate, from the coordinate you can do it. But the thing is that you can go for some Kinect devices, and from that you can capture this data. And so here there is no record for any biomarkers kind of things.
Any other question from the participant side? Okay, so if there is no question, then I would like to thank you, Professor Anup Nandy, for giving a insightful lecture. He has explained the gate analysis and explained many AI-driven multi-sensor techniques and explain it with the result and many other techniques. So we would like to thank you, sir, and thank you for accepting our invitation on a very short notice. Thank you, sir.
Thank you so much, sir. Okay. Okay, sir. Sir, I am signing out. Okay, sir.
Yeah, please, sir. Thank you, sir.
Thank you, sir.
So now, our 2 days before lunch session has been completed. So there is a lunch break now, and we will join by 2 o'clock. And after lunch at 2 o'clock, there will be a practical session. So it will be good if you are having a laptop or like system which where you can do the coding in Python. So our expert Dr. Aditi will explain you from the basic, like it doesn't matter like you are having that expertise or not. So we will start from the basic, and will also request you to implement the same at the same time. And if you will be having some problem or if any doubt, then you can interrupt in between and can discuss. So that will be completely interactive session. So it will be more beneficial if you are having a laptop or any system where you can do the coding. However, I understand that you are able to see it on the desktop. However, the problem can be there where the participants are using the mobile phone. If you are using a mobile phone, then also use the desktop or any laptop so that you will be able to do it. Okay, thank you. Thank you all. We will join by 2 o'clock. So if any query or if anyone want to say anything, can say. यदि किसी को कोई डाउट या कुछ भी है, we can discuss. Okay. So So about the like one question in the chat box about the recording. After the completion of this workshop, we will share the recording. And what will be the practice today? We will start from the basic, and the session speed will be depending on the participant. If participants are very responsive and doing the things very quickly, then we'll go at the higher level. But see how much cooperation is there from the participant side. So at that way we will see, right? So thank you very much for attending. So we will be joining by 2 o'clock. Thank you.